We're going to go over the main purpose and the basic operations on calculating quartiles and percentiles for sets of data. We will use a random sample of 60 different northern cardinal call lengths measured in seconds, and these were obtained from a certain region. Quartiles and percentiles help us understand the distribution of sets of data. Here we have a number line graph of all of the 60 call lengths. A few of the values are duplicates, and so some of the dots are on top of each other. If you tried to count all 60, you might not be able to see all 60 because some are plotted on top of each other. We can see that this set of data is fairly evenly spread out, but there is some clumping, and the very short call lengths are less frequent. The lower values are more spread out than the higher values. We will discuss quartiles first. Quartiles cut a set of data into 4 equal-sized subsets, and it's important to note that the data needs to be ordered from lowest to highest. And then the 4 subsets have some meaning to them. You have a lowest quarter of the data, 2 middle quarters of the data, and then a highest quarter of the data. Percentiles demark a value at which a certain percent falls at or below that value. For example, if you find the 85th percentile of a set of data, 85% of the data will fall at or below what is the 85th percentile. We will use relatively small sets of data in our lessons for just ease of handling, but in general, quartiles and percentiles make more sense to reference when sets of data are very large and are somewhat representative as a sample of a larger population. The very precise interpolating approach we are taking to find percentiles also makes more sense for large sets of data that represent a sample from a larger population with continuous data. Remember, data can be discrete or continuous. Discrete data means there's definite gaps in between possible values. Continuous data means values could take on any number in between a certain interval. So for example, the time at which swimmers finish a race is really continuous data, but ACT scores would be discrete data. Consider a company that has a random sample of 1,200 salaries offered for a certain type of job. They might take that set of data and sort them, find the quartiles, and then set their job offer at the 3rd quartile, offering more than average to get better candidates, but not so high that they're overpaying. That would be a good use of quartiles. Or consider a football team considering to add cornerbacks to their roster. They might have a sample of 500 times at which players trying out ran the 40-yard dash. They might set their boundary of acceptance at the 40th percentile, meaning they're only interested in the 40% of players that have the faster times. So let's dig into how to find quartiles. Remember, quartiles cut a set of data into 4 equal subsets. So the first step is actually to find the 2nd quartile, also called the median. We find the median position, so where it is in the data, by averaging the first and last position. How do you average any numbers? You add them and divide by however many you have. If we're averaging 2 numbers, we're going to add them and divide by 2. So we're trying to find the average, the middle position between 1 which represents our first number, and n, which represents our last number. So 1 plus n divided by 2 is always how to find the position of the second quartile. So let us find the position of the second quartile, also called the median, for our set of 60 northern cardinal call times. The first position is 1, and the last position is 60. 1 plus 60 is 61. 61 divided by 2 is 30.5. So the position of the median or second quartile for this set of data is in between the 30th and 31st value. The position is 30.5, which means we're going to find the average between the 30 and the 31st value. For this set of data, the 30th value was 2.75 seconds and the 31st value was 2.78 seconds. The median is going to be exactly halfway in between those two values. So average the 30th and the 31st value, so 2.75 gets added to 2.78, and we divide by 2 because we're averaging those two amounts of seconds, and we get 2.765 seconds. So the very middle of the data is 2.765 seconds. Here we have marked on our number line graph where the median falls. We've marked in between the 30th and 31st data value at 2.765 seconds. Notice the lower half of the data is more spread out and the upper half of the data is more compact, more clumped together. We would say that this set of data is slightly skewed to the left. The lower values are more spread out. And if we did find the mean would be a little bit lower than the value that we found for the median. The first quartile is in the middle of the lower half of the data. So we want to find where the middle is for the lower half of the data. So average the first position with the position immediately before the median or the second quartile. So remember, for this set of data, the second quartile was at 30.5, meaning it was in between the 30th and the 31st. So average 1 and 30, and you get 15.5. That tells you that the first quartile is located halfway between the 15th and 16th value. The first quartile is the middle of the lower half of the data, and we said it should be at position 15.5. So that means we're going to average the 15th and 16th value to find exactly halfway in between them. The 15th value, if you look at the set of data, is 2.1, and the 16th value is 2.17. If I add those together and divide by 2, I get 2.135. So the value of the first quartile is 2.135 seconds. That is the number that cuts off the lower 1/4 of the data. The third quartile is right in the middle of the upper half of the data. So we need to find the position for the middle of the upper half of the data. The last value in the data is 60, and the value immediately after the median is 31st. So average 31 and 60, and you get 45.5. So the position of the third quartile of this set of data is 45.5. That means we're going to take the 45th value and the 46th value and average them to get a value halfway in between the two of them. So the 45th value is 3.35, the 46th value is 3.36, halfway in between the two is 3.355 seconds. So 3.355 seconds is considered the third quartile, And our data is now cut into 4 equal-sized subsets. So here are our 4 quarters of data. This particular set of data is cut into 4 sets of 15 data values, and the quartiles divide where those subsets begin and end. Once you have found your quartiles, you can list what is called the 5-number summary, and it includes the minimum, the very lowest value, the maximum, which is the very highest value, the first quartile, the second quartile, and the third quartile. And often we make a nice little graph called a box and whisker plot that sort of draws a picture of the set of data for us with this 5-number summary. So here we have the box and whisker plot drawn for our bird call times, and you could see that the whisker that goes down to the minimum value is a little bit longer than the whisker that goes up to the maximum value. We talked about that earlier when we saw the number line graph of the data, that the data seemed a little more spread out on the lower end. The middle part of the data is relatively uniform, but between Q2 and Q3 is a little bit more narrow than between Q2 and Q1. Again, the lower half of the data is a little bit more spread out. We would say that this data is skewed to the left towards the lower values, and the mean would be a little bit lower than our median of 2.765 seconds. Another value that we sometimes find useful is called the interquartile range, and it is how spread out Q3 is from Q1. So you take Q3 and you subtract Q1, the third quartile minus the first quartile. In this case, we would get an interquartile range of 1.22 seconds. Percentiles demark a value at which a certain percent falls at or below the value. Let's start by finding the 85th percentile for this set of data. To find the 85th percentile, first find where it is in the data. So 85% in its working decimal form is 0.85. Multiply 0.85 by the size of the data set, which is 60, and we get 51. The 51st value in the data set, sorted from low to high, is the 85th percentile. 51 values fall at or below that number, and that's 85% of the data. Note that 51 divided by 60 gives us 0.85. So in general, to find the position of a percentile, turn your percentile into its decimal form by dividing by 100, and multiply that by the number of values in your data set. In this case, we did 0.85 to find the 85th percentile times 60 because we had 60 data values. Our 51st value was 3.5 seconds, so 85% of the data falls at or below 3.5 seconds. So we're showing the 85% of the data here on the screen. So 85% are falling at or below 3.5 seconds. Let us do another example of percentiles with this set of data. Let's find the 30th percentile. So 30% in its working decimal form is 0.30. Multiply by our sample size of 60, and we get 18. The 18th value is our 30th percentile. 30% of the data falls at or below that value, which turns out to be 2.19 seconds. So 30% of the data falls at or below 2.19 seconds. Let's look at an interesting percentile of 75%. And so 75% times 60 is 45. So the 45th value is the 75th percentile. 45 or 75% of the data falls at or below 3.35 seconds. Now remember, we found the third quartile to be in between the 45th and 46th value. That was in order to cut the data exactly into 4 equal subsets. So to do that, we had to average the 45th and 46th value. The third quartile and the 75th percentile are always going to be close, but just by the definitions, they'll usually be slightly off from each other. The 25th percentile and the first quartile also will be close, but slightly off from each other for most sets of data. In this case, 25% of 60 is 15, so the 15th value is the 25th percentile. 25% of the data falls at or below that value. But the first quartile was slightly more. It was halfway in between the 15th and 16th in order to cut the data into exactly 4 equal pieces. The 50th percentile will also be slightly different than the median. In this case, it would have been the 30th value, which was 2.75. So again, the 25th, 50th, and 75th percentiles will always be close to the quartiles. Sometimes some people will just round off the two so that they're the same things. But technically, because you're trying to quarter the data, you usually get slightly different values when you actually quarter the data to find the quartiles. Our other examples of percentiles had us land exactly on one of the data values, but that doesn't always happen. Consider the 44th percentile. 44% times 60 is 26.4 as the position. So that means the 44th percentile is in between the 26th and the 27th. But it's not exactly halfway between them. We got 0.4 as the decimal and not 0.5. So we're going to find where 0.4 of the distance is between the 26th and 27th value. So find the 26th and 27th value and then find how far apart they are. The 27th value was 2.69, the 26th was 2.66, subtract, and you get 0.03. So 0.4 of 0.03 should get added then to 2.66, and that gives you a value of 2.672 seconds. So the 44th percentile for this set of data is 2.672 seconds, in between the 26th and 27th, but slightly closer to the 26th value. Again, if somebody wanted to just round down to the 26th value when they're stating the 44th percentile, it's probably not a big idea, but we're trying to be very precise because if there are some occasions where it's helpful to be very precise, you now understand how to do that. So here we're studying lengths of time of bird calls, and that is continuous data. And this could be considered a random sample of a very large population of bird calls. We could state that in general, 44% of northern cardinal calls in this region fall at or below 2.672 seconds. If you took a smaller sample and found, for example, the 44th percentile using interpolating, and then found a much larger sample and found the 44th percentile of the larger sample, you would likely find your 44th percentile from the smaller sample more accurate to the 44th percentile of the larger sample than if you had rounded down or up to the nearest value. So using our example, we interpolated and got 2.672 seconds. If we had a very large sample and found the 44th percentile, likely the 44th percentile is going to be closer to 2.672 seconds than if we had rounded down to 2.66 seconds. Here we have a set of 53 weights of cutie tangerines measured in ounces. So it's a random sample of 53 tangerines of the brand Cutie measured in ounces. Why don't you pause the video and try to work through finding the quartiles and the 65th percentile, the 90th percentile, and the 5th percentile, and see if you understand how to arrive at the values that are listed here. And later, we'll kind of work through where the values come from. Let's work through the quartiles first. So remember, when you're finding quartiles, find the median first. It's the very middle of the data. We had 53 values, so the position of the median should be 1 plus 53 divided by 2. That gives us 27. So the 27th value is the median, and that is 2.43 ounces. Then the first quartile is in the middle of the lower half of the data. 26 is immediately before 27, so average 1 and 26, and you get 13.5. That's the position of the first quartile. The 13th value is 2.01, the 14th value is 2.05, average those, and you get 2.03 ounces. So the first quartile is at the 13.5 position and is 2.03 ounces. The third quartile is the middle of the upper half of the data. 28 is immediately after 27, so average 28 position with the last position of 53, and you get 40.5 as the position of the third quartile. So take the 40th value and the 41st value and average them. Now for this set of data, the 40th and 41st value were the exact same thing, 2.85 ounces. So when you average them, you still get 2.85 ounces. For the 65th percentile, 65% of 53 is 34.45. So you're going to get a value in between the 34th and 35th, like almost in halfway in between them, but technically we'll find 34.45. So the 34th value was 2.65 and the 35th value was 2.66. So the difference between those two values gets multiplied by the 0.45 in the 34.45, and then you add that extra little bit to the 34th value. So 2.65 was the 34th value. You're going to put 45% of the distance between it and the 35th, and that gives you 2.6545 ounces. For the 90th percentile, 90% of 53 is 47.7. So find the 47th and 48th values, and then you're going to move 0.7 of the distance between them to get the actual percentile. So the 47th value was 3.06 and the 48th value is 3.07. So 3.06 add 0.7 times the difference between those two, and you get 3.067 ounces. So in between the 47th and 48th, a little bit closer to the 48th value. The 5th percentile will have position 2.65 because you multiply 5% by 53, you get 2.65. So find the second and third values, which is 1.82 for the third and 1.79 for the second, and take 65% of the distance between them and add it to the second value, and you get a number in between the second and third values, 1.8095 ounces. So that was a good few examples of how to find interpolated values. Adding some meaning to the values we just found, since weights of tangerines are continuous data, and this could be considered a random sample from a larger population of tangerines from this company, we could say that 65% of the tangerines from this company fall at or below 2.6545 ounces. And 90% fall at or below 3.067 ounces. Whereas only 5% fall at or below 1.8095 ounces. I hope you enjoyed your tour through quartiles and percentiles. You may find slightly different variations on how to find these values. In the long run, when everybody rounds, the values turn out to be about the same, but I stuck to kind of the one main definition. Quartiles quarter your data, just like there's 4 quarters in a dollar that are all worth 25 cents. There's 4 quarters in a football game that are all worth the same amount of time. And then percentiles, I went through a very precise method. If you need to be precise, you now know how to be. If you don't need to be, you could always round. So anyway, go off and practice and sing a happy tune.